Welcome, everyone, to this Tuesday, June 12th edition of the Daily Space. Now, today's news is perhaps best described as, these are not things that I ever expected to see in astrophysics journals as being picked up. And so I invite you to join me on a very strange science fiction reality that is our actual reality for today. So this is a daily news show that brings you the latest in astronomy and space science news. It really is. It really, really is. Nonetheless, this is a paper that I encountered this morning, and so sorry, I will fix the alignment on that. So this particular article that I encountered this morning was heavy sterile neutrinos in stellar core collapse. And I'm like, heavy sterile neutrinos are not a thing. Why are you writing this research paper on something that isn't a thing? And so I did some Googling, and it turns out that last week there was a bit of news and a bit of publication around some anomalous detections that could potentially, maybe sort of, if you squint your eyes, maybe further data needed, be explained with sterile neutrinos. Now, for those of you who don't know what a neutrino is, what a sterile neutrino is, that's okay. This is why I'm here. In a lot of different nuclear reactions, you have bits of energy, bits of particles, all given off. And the role of these things that are given off is to conserve things like charge, spin, mass. There's lots of different factors that have to be constrained to keep our universe in balance. And one of the particles that gets created in a variety of different reactions is a kind of particle called a neutrino. They come in different varieties. Reactions involving electrons produce electron neutrinos. Reactions involving tau particles produce tau neutrinos. Muon reactions produce mu neutrinos. And through a fluke of nature, these different kinds of particles have the ability to change identity. They have a little bit of mass, and by converting back and forth between the energy the particle has, this includes how fast it's moving and things like that, by converting mass and energy back and forth, an electron neutrino can decide, hey, I'd like to be a bit fatter now and become a tau neutrino. A tau neutrino can say, hey, I'd like to be skinnier and move faster and become an electron neutrino. Now, this doesn't actually happen with purpose. This is just the flukes of probability and mathematics. Now, it's theorized that certain reactions where we see a excess of electron neutrinos, more electron neutrinos than we would expect from the reactions that took place, that maybe there's this additional fourth kind of neutrino that weighs a lot more, or has more mass is the correct way to say it, that has a lot more mass. Maybe it's created as well. And this sterile neutrino could potentially be a kind of dark matter particle, something that doesn't interact except via gravity, and has the ability, like the other three kinds of neutrinos, to switch identities. This consideration that maybe these anomalous numbers of detected neutrinos come from the creation of a fourth kind of neutrino is intriguing, it's interesting, it's not required by the data. Now, of course, as soon as this sterile neutrino data came out, we had theorists rerunning their, thank you, Guido, for the subscription. As soon as we had the sterile neutrino results announced, we had folks saying, hey, let's rerun our computer models and see how this affects various kinds of star models. So here we go down the rabbit hole, exploring possibilities of physics with new particles. Now, if I sound a bit like a curmudgeon about this, it's because extraordinary results need extraordinary data to be believed. I'm going to always be a curmudgeon with results that require us to throw out our standard model of particle physics, which doesn't require or even really allow the sterile neutrino to exist. So until we have this extraordinary results, I will share the news with you, but I'm going to be a curmudgeon because I want the data. So moving on to our next story of Dear Physics, What Are You Doing to Me? This particular result, I'm going to bring up and actually show you the press release itself in a moment. So this is a pretty awesome image, and my eye was drawn to the image, and then my brain was a bit broken by the title. The title was Wormhole Echoes That May Revolutionize Astrophysics. Now, wormholes, as mathematically theorized, collapse the moment any particles, any mass, any energy enters them. These are a theoretical, mathematical thing that, as near as we can tell, doesn't exist in the real world. And here is a press release saying wormholes could explain black hole collisions as observed by LIGO. Now, the science that they're using is that if wormholes exist, they're going to have a different kind of interface to the main universe than black holes do. Black holes have a hard event horizon, and when black hole mergers occur, we have to deal with both the merger of the mass inside the event horizon and the event horizon itself. And this kind of a merger will appear as the initial gravitational wave that we detect, and then there should be a hard stop to this because of that event horizon. Now, with a wormhole kind of event, what would happen instead is you'd have the merger. There is no hard-edged event horizon, and we should be able to detect echoes to the gravitational wave the same way you might hear echoes when you drop something into a well as the sound waves reverberate multiple times. They are saying that we need to keep listening, we need further data, we need observations. This is an idea, this is not confirmation of anything. It's intriguing. I maintain wormholes are supposed to collapse when mass enters them. We've been looking for black hole collisions for a long time. We predicted what they should sound like, or at least how they should resonate. And our observations meet our expectations. Why are you coming up with this theory now? It's a legitimate theory. I can't push it out the window and say, bye-bye, not yet. More data is needed. And this is one of the uncomfortable things about being a scientist, is if the data for this is found, if we do see those echoes in the data, I have to be willing to admit, well, wormholes just might be out there. So stay tuned, and hopefully we will get more data that allows us to either push this idea out the window or forces us to grab hold and say, okay, let's get more data, and this is the direction we're headed in following the observations. Now, in more comfortable news, we do have a new paper coming out saying that a 2 Earth radius planet has been found orbiting a bright nearby red dwarf star. This is the K-dwarf Wolf 503. It's just a happy little tiny result. This particular team found this particular planet in the Kepler data. like I said, it's just 2 Earth radius in size. So this is not an Earth-like planet. This is not potentially a habitable planet in the way we know. This is just a planet that is only located about 130 light years away, and it's small, and we need more small worlds to better understand the frequency at which different planet sizes exist. So that sounded like a really odd statement, so let me unpack it a little bit. Until recently, we've only had the ability to detect the biggest planets. Thank you so much for the cheer, Astro Helge. That is awesome. So until recently, we only had the capacity to detect the biggest planets. And when you can only detect the biggest planets, that doesn't tell you about anything else. It's sort of like, for the longest time, we only had dinosaur bones for adult dinosaurs, and we didn't know anything about baby dinosaurs. Well, as we've gotten better at fossil hunting, we've found baby dinosaurs. And as we've got better at planet hunting, we've found lower mass, smaller radius planets. By finding more and more of these, by being able to say, we have sampled and can tell you within the following limits there are or are not small planets at, well, the same distances we find our own terrestrial planets orbiting other stars. This allows us to understand how frequently do we have hot Jupiters? Are they really the most common solar system out there? How frequently do we have terrestrial planets? It's all kind of awesome. So go, small planet finders, go, and help us map out the distribution of worlds in our universe. So on this happy little 2 Earth radius planet, I'm going to end this episode of Daily Space and go to taking your questions. Once again, I am Dr. Pamela Gay. I am your host. The Daily Space is brought to you by CosmoQuest. We are a multi-institutional collaboration led by the Astronomical Society of the Pacific. Here at the Daily Space, we bring you the day's astronomy and space science news Monday through Friday right here on Twitch. If you like what you see, please give us a follow. And if you really want to keep seeing what you see, well, sustain our efforts through your subscriptions and through your bits. Thank you so much, and I will take your questions. Let me pull over a bigger version of the chat. So I see folks asking, do we know the mass of the world? I'm not seeing it listed in this particular article. In order to get at the mass, we have to be able to measure the radial velocity of the star. I don't know if these observations have been made yet. So what I'm seeing in the article is the 2 Earth radius. So, and once again, I would just like to thank the folks who joined us this month and supported us this week. Guido, thank you for subscribing for a second month. Astro Helge, thank you so much. Your awesomeness is overwhelming. Thank you so much for the follow, Ed Thompson. So looking to see if there's new questions. Yes, Automod deserves to be laughed at. Got a link to the wormhole story. Why, yes, I do. Let me share that into the chat. And I'm also going to share with you an older astrophysics paper explaining a little bit more on the physics of this. Maybe I'm not going to. Hold on. Let me find it somewhere else. Still looking for the link. I have have it here somewhere. There it is. So this is the science fair, the science paper, not science fair, the science paper that I used to try and digest things. Are there any other questions? So tomorrow I will be back once again. But before then, tonight I'm going to be streaming right here on this channel at 9 p.m. Eastern. That is 6 p.m. Pacific, 11 a.m. tomorrow in Australia. And I will be working on continuing to destroy a hot Jupiter as it orbits a star. Right now I'm actually still in the getting it to orbit properly stage, but that's where I'm going. So I see Hanny's Verb asking, could a quasar make heavier elements in the early universe? Well, in general, quasars, not so much the black hole in the center, but the accretion disk around them, do undergo different kinds of nuclear reactions. This is why they light up so brightly. I have to admit, I haven't looked recently to see exactly what all is being created in a quasar. I don't think in general they're undergoing the kinds of reactions that make large amounts of heavy elements. But they are generating elements. But those elements are all like on their way into the supermassive black hole. So I don't think this would be a productive way of making heavy elements that we can usefully recycle. So Michael, what you were talking about, this idea that wormholes and black holes are intrinsically related and the wormholes connect to another universe. This is an idea that's been kicking around for a long time. It's not a dominant theory. This is where language gets ugly. We have capital T theories like gravity that are accepted. They are real. No one's going to argue gravity isn't the thing. Then we have the lowercase t theories. These are the I have a theory that I'm trying to think of one that hasn't been proved that is completely rational. I think that the lowercase t theories that say that Saturn's rings are fairly young are halfway reasonable. Those are lowercase t theories that are neither confirmed nor denied. We're waiting for further evidence, and they're cool. No one is going to attack someone for having one of these theories and say they're doing bad science. And then there's the theories out there that we raise an eyebrow at, go, well, I can't say that it's wrong, but we need data. And the idea that black holes and wormholes are intrinsically related and connect to other universes, however briefly, is one of those ones that you raise an eyebrow at and wait to see what happens, but you can't disprove. I don't know if that made a lot of sense, but this is how I keep up on these things. Okay, Peter, I will scroll up for those additional questions. Scrolling. Okay. So I see, Peter, do neutrinos move faster than light? No. Neutrinos have mass. They move slower than light. Nothing moves faster than light. Neutrinos just have this fairly interesting way of switching between energy and mass. Yeah, I'm not going into white holes. That is a language of theoretical physics that I just basically kind of go, no. No observational evidence. Observational evidence is something that I'm kind of big on. Looking to see if there's other questions. So Peter's asking, can we travel to the Pegasus galaxy through a white hole? No. But good question. I can see what you did there. So yes, it is a mathematical result, Michael. There are lots of things that you can do with maths that are pretty intriguing. And this is where the question becomes, where do you demand the line be drawn between what's mathematically possible and reality. Because for a while, relativity was a mathematical possibility that hadn't yet been proven. So we need to try and figure out, what do we discuss as we need this theory to be true? Like, if there is a particle explanation for gravity, we need gravitons to be true. We have no way of detecting those. So it's complicated. So there's just no observational evidence, Hanny. And when you look at the maths, you run into, with wormholes at least, this problem of if mass falls into them, which mass energy is a dichotomy, which means if a cosmic microwave background photon falls into them, they collapse. So yeah. Anyways, I am about to have a meeting, so I need to end this just a few minutes early. It has, as always, been wonderful chatting with all of you, and I hope I will see you this evening when I work on shredding planets, orbiting stars, using software, and making pretty pictures that make us hopefully laugh as we go. So wherever you are in this world, have a wonderful morning, evening, or afternoon, and remember, look up. Bye-bye.